Hey, welcome everybody. This is Math 1332 video lesson, Chapter 3, Section 7. Section 7 deals with arguments and their truth tables. In this section, we're going to learn what an argument is and how to use truth tables to prove whether an argument is valid or invalid. And then, hopefully by the end, that once we prove these initial theorems, then you don't have to repeat the whole process every time. Once you recognize a pattern, then you just say, okay, it's valid or invalid because of this reason. Argument is made up of two parts. First part is the given element or the given statement. This is called a premise. And then the conclusion. Or premises. An argument is valid. This is the interesting part. An argument is valid if all of the resulting truth elements on the truth table are true. So the very last column of your truth table, if they're all true, then it's a valid argument. And whenever the last comment, all the conclusions are true, we call that a tautology. All conclusions are true. All right. An argument that is not valid is called an invalid argument, or a fallacy. An argument with true premises is called a sound argument. All right, now, so how do we test the validity of an argument? test the validity of an argument we create a truth table. But here's the important part. Remember, the argument is made up of premises and then comes to a conclusion. So it has to be in a conditional statement. To test the validity, we create a truth table. But what goes in the truth table? You have to take premise. I'll take all the premises and connect them with the and statement. So premise 1, premise 2, and however many premises you have, premise n. Take all of those, connect them with the and. And that's your first part. Then it has to be in a conditional statement. If all of these are true, then the conclusion is true. So you take all your premises, create an and statement, that's your premise, and your conclusion. So if these are all true, then that's true. So that's how you test to see if a statement is valid or invalid. So let's take a look at these. Let's look at valid ones first. I was going to do invalid, but I'll shoot valid. Let's see what valid ones look like first. These are sound and proven arguments that are valid. So once you see that a statement that's given to you in a question, if it's given as in one of these 4 possibilities, you don't have to do the truth table. You can just go ahead and connect it to these, and you're done. So the first valid statement, argument, I mean, if P, then Q. And you're given this argument P. That therefore Q. If P, then Q. If it's raining outside, then if it's cloudy outside, then it's rain. It's going to rain. It's cloudy, therefore it's going to rain. This is called an argument of direct reasoning. This is one of the oldest ones. This one started out back in Aristotle, when first started discussing logic and forms of logic. In Latin, it's called modus ponens. Modus means method, ponens means direct. So direct methods. The next one we have is if P, then Q. If not Q, therefore not P. If it's cloudy outside, then it will rain. If it's not raining outside, then it's not cloudy. This is called contrapositive reasoning. if you notice, it's the reverse of it. So that in Latin, Aristotle called this modus tollens. You have two more. Using the or statement, P or Q. If not P, therefore Q. And similarly, P or Q. If not Q, therefore P. Because or, to be true, you have to pick either of them. You want the car or what's behind door number 1. I don't want the car, so I'm going to take door number 1. Car or door number 1. I don't want door number 1, so I'll take the car. This is called disjunctive reasoning. If you don't pick one of the first option, then you'll take the second. If you pick the second, then you'll take the third. So, the first. And the last of the valid ones. You've probably seen this one before. If P, then Q. If Q, then R. Therefore, if P, then R. If P, then Q, then if Q, then R, then P, then R. If A is B and B is C, then A is C. This is called transitive reasoning. You can transfer logic from one to another. So if A is B and B is C, then A is C. We can also look at the negation of them, the contrapositive of it. If not R, then not P. If A is B and B is C, then if I don't have C, then I didn't have A. So these are all the valid arguments. If you see any of these patterns, then you know your truth tables on the very last column will be true. We also have some invalid arguments. But if you see these, again, you don't have to do the work. You just state that, hey, it doesn't work, it's false. The first one. If P, then Q, and Q, therefore P. So that one's going, looking at the direct reasoning. It's saying that if P, then Q, and Q, then it has to be P. If it's Tuesday, then it's raining. It's raining, it has to be Tuesday. No, it could be Sunday. It could be raining on Sunday also. This is called the fallacy of the converse. Okay, then we have similar to that. If P, then Q, and not P, therefore not Q. So, it just says if P, then Q. If I don't take P, then I don't take Q. There's maybe other ways of getting it. This is called the fallacy of the inverse. P or Q, then P, and P, then not Q. If I have A or B, and I've took A, doesn't mean that didn't take B, and won't take B. That's just that you can't be sure of that. They could be the same thing. Or we could look at P or Q. If I choose Q, you can't say that it's not P. That's called the error of disjunctive reasoning. We're going to show proofs of these in a little bit. I'll show you how to prove. We'll pick one of them, and I'll show you how to do a truth table with these. And the last one. If P, then Q. If Q, then R. Therefore, if R, then P. If A equals B and B equals C, then C equals A. No. These could be sets. If A is inside B and B is inside C, that doesn't mean that C is inside A, the set of numbers. Or we could look at the contrapositive of it. If not P, then not R. Again, you can't do that reasoning because of, just because you don't have one thing doesn't mean you can't have the other. This is called the error of transitive reasoning. Okay, well, let's see these. Let's do a truth table for these. Not all of them. We're going to do one or two of them. So let's do the first one. Let's do the direct reasoning. Modus ponens. We had this statement. Let's prove this one is valid. The way you prove if it's valid, take the premises. This is premise 1, this is premise 2, this is the conclusion. So we have to take premise 1 and we have to take premise 2 and see if that leads to the conclusion. So if P then Q and P, then does that lead to Q? So let's create the truth table. So we have true, 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 false, false, true, false, false. So the first one to look at, let's do this one. If P, then Q. Remember, the if then is the valley. True, true, false, false. It's only false if it goes from true to false. If it stays the same, it's good. So true, true is true. True, false, it's going down, so it's false. False, true, going up, so it's good. True. False, false, staying the same, so it's true. So that's the first part. Now let's do if P, then Q, and P. So we're looking at this column and this one. It's an and statement. True and true. That's the straight pipe, so they both have to be on to be working. If one of them are closed, then it doesn't work. Now let's look at the entire statement. If P, then Q, and P, then Q. So we'll look at the second column and the fourth column. It's a conditional statement. So true to true, that's true. False to false, that's true. False to true, true. False to false, that's true. So because all of these are true, it's a valid argument. Let's look at an example of an invalid argument. If P, then Q, not P, therefore not Q. We're looking at the fallacy of the inverse. So we have to take the first premise. This is premise 1, premise 2, and conclusion. So the premise 1 and premise 2, and see if it reaches conclusion. So premise 1 is if P then Q and not P. We have to do all that first. If all that, then not Q. So you see here, that goes in there, that goes in there, and the conclusion goes at the end. So let's create our truth table, P and Q. Again, since we have two elements, 2 to the power 2, we'll have 4 rows. Because we have 2 elements. So the possibilities are they both be true, true and false, false and true, false and false. Think of light switches in a room. They could both be on. One could be on, one could be off. The other one could be off, then on, or they could both be off. So look at our statement here. Our first thing we have to do is if P, then Q. If true, then true, true. If true, then false is false. False, then true is true. False and false is true. We only have to find not P. We have to figure out this one. So not P is just the opposite of the P's. So it's false, false, true, true. So let's do the entire inside. If P, then Q, and not P. Remember, the AND statement is that single pipe. If the valve, one valve is open, that's true. If it's closed, it's false. So we'll look at these 2 columns. Open, closed, it doesn't work. Closed, closed, water won't come out. Open, open, water will come out. Open, open, water will come out. So that's this whole thing here. Now we have to figure out not Q. So that goes back over here to the Q column, and we just change the sign, change the symbols from false to true, true to false. Now let's put everything together. If P, then Q, and not P, then not Q. So if F, then F, that's true. F, then T, that's true. T and F is F. T and T is true. Because of that one, this is an invalid argument. Alright, so that's what we're going to have to do when we solve homework problems here. Alright, let's go do the homework now. See you in a bit.